So, in geometry, at the beginning of this class, I told you guys that trig functions in general are designed to work with right triangles. We talked about how to set up the right triangles using opposite, adjacent, and hypotenuse to define those triangles. And that is largely true. For a significant portion of trigonometry, everything revolves around right triangles and right triangle math. We use the unit circle to create triangles to find missing values. We use these triangles to set up different trigonometric functions and find identities for them. We use right triangles to do things like double angle formulas, half angle formulas, sum to product, product of sums. Lots of trig functions, lots of triangles. However, today, tomorrow, and next week, we're looking at two laws that apply to all triangles. Now, these two laws allow us to look at non-right triangles, which, in fact, is one of our first definitions. Oblique triangles.
Wait, what's that in the bottom right hand corner of the triangle? What is that?
I'll tell you in a second.
No, it has the right.
Gamma.
That's a Y.
Gamma.
But it's a Y.
Gamma.
Wait, make it bigger.
Woogie boogie.
Boogie boogie.
A gamma looks like a Y with a loop at the end.
Sure.
So, gamma. All right, an oblique triangle is a non-right triangle. Now, as we discussed a moment ago, most trig functions, sine, cosine, tangent, even the more advanced ones, cosecant, secant, and cotangent, revolve around sides of a right triangle. We talk about sine being opposite of our hypotenuse, but those terms apply specifically to right triangles. They have to have an opposite side, they have to have a hypotenuse, they have to have an adjacent side. An oblique triangle is one that does not match that mold. It is not right. It can either be an obtuse triangle, it could be an acute triangle. Those are terminologies primarily used in geometry. But really, we just focus upon the term oblique to mean everything else. If it's not right, it's oblique. Now, all oblique triangles have a unique property about them, which is that they can be turned into right triangles if you are kind of creative. They use a process referred to as an altitude. An altitude represents a height within a triangle created using a right angle.
Damn, how do you feel, bro?
Go kill it.
I'm sorry. Was that loud?
Yes.
Sorry.
An altitude is a height within a triangle created using a right angle. Now, there's actually multiple heights in many different triangles. And so any given triangle, any oblique triangle, can be turned into multiple right triangles using an altitude. Here's an example. If I draw, for example, this triangle. Ooh. Clearly not a right triangle, right? None of the angles are 90 degrees. I don't see that 90 degree symbol from geometry in any of these angles. I can turn this into two right triangles and thereby apply trig to it by drawing an altitude. Now again, the altitude is representative typically of a height within the triangle created using a right angle. You can also create altitudes outside, but that's not our main focus for this section. So, to create an altitude in this picture, first of all, this right here is considered to be oblique. Why is it oblique? There's no right angle. So it's got to be oblique. So where's my altitude? Well, there's actually three of them for this picture, but let's focus on the main one, going straight up and down, creating a right angle to the bottom. This will take this oblique triangle and turn it into two right triangles. Now the thing is, each of these right triangles could apply trig functions to them because they are now right triangles. I could talk about sine of the left triangle. I could talk about sine of the right triangle. I could talk about cosine of the left triangle. I could talk about cosine of the right triangle. I could talk about tangent, cotangent, secant, cosecant, cotangent. Any of them I could talk about for each of these smaller triangles. But what I can't do is talk about sine of the big triangle because it's not right. I can't talk about cosine of the big triangle because it is not right. I cannot talk about tangent of the big triangle because it is not right. What I can talk about are two laws. These laws involve a trig function, but do not represent the function of the entire triangle. Here are the two laws. This week, let's focus on law number 1, the law of sines. Now, you'll notice that in my picture up here, I have 3 sides and 3 angles talked about. The 3 sides are A, B, and C. The 3 angles, you notice, are opposite their respective sides. A is opposite of alpha, B is opposite of beta, and C is opposite this new angle, which we call gamma. In the Greek alphabet, gamma comes third. Why not a C letter? I don't know. So, alpha, beta, gamma, each opposite A, B, and C respectively. Now, the law of sine states that sine of alpha divided by A equals sine of beta divided by B, which is sine of gamma over C. Where's my loop? There's my loop.
Yeah, I thought we didn't go over everything on our cheat sheet.
Yep.
Then we went over everything. I was like, this is wrong. I thought we didn't go over.
Law of sine and law of cosine, the last piece on the cheat sheet. It's almost like that cheat sheet's the whole class. Law of sine. Now notice, this is a 3-part equality statement. You can use any 2 of these to set up a standard equation. But all 3 of them can be true and are true for any oblique triangle. Ironically, it's also true for any right triangle. If you set up a right triangle with these same 3 pieces marked, you can still use the law of sines on a right triangle. It's just you don't really need to because you have the other trig functions to work with instead. You could just use tangent. You could just use cosine. You could just use sine by itself. You don't need anything fancier than that. But for oblique triangles, the law of sines allows us to set up an equation. Now, the point of the law of sines is quite simple. It will allow us to find missing values. Nice touch base there. So, the purpose of the law of sines is to find missing values. How we do that is by setting up one of these sets of equations. In preparation for today, there is a couple properties of algebra and a couple properties of geometry that will be helpful for some of our problems. Let's go back to geometry for a second. And remember one of my favorite theorems from geometry, the triangle, angle, sum theorem. This one, quite beneficial for some problems today, because you will not be finished with a problem today until you know the values for all 3 sides and the values for all 3 angles. One more time. You are not finished today until you know the value of all 3 sides and all 3 angles. The law of sines will help us find that, but to do so, let's pull up some pieces that might be helpful from other classes. Triangle, angle, sum theorem. Those of you guys that remember geometry pretty well, what was the triangle, angle, sum theorem? Correct. So in this case, for this specific picture, I want to write it in a very specific way. This would imply that alpha plus beta plus gamma has to equal 180 degrees. The triangle, angle, sum theorem. We'll use this a fair bit today because while the law of sines can find specific values, it also doesn't have to be used every time. I can instead use this formula to find a missing angle. So the triangle, angle, sum theorem. Beautiful one to help us out today. Make sure you have that for your notes if you don't remember it yourself. Second one. If I wish to determine an angle naturally, so this would be a trig idea, I can use an inverse. As a reminder from, what was that, chapter 7? When it comes to an inverse states that if sine of alpha equals a over b, then sine inverse of a over b equals alpha. In other words, an inverse undoes the sine function, or the cosine function, or the tangent function. They're opposites of each other. The final thing is an algebra topic to be helpful today. If I have two fractions that are equal to each other, it's referred to as a cross product. If I have two fractions that are equal to each other, so I have A over B equals C over D. If I have two fractions that are equal, I may form a cross product to get rid of the fractions. How do I do that? Well, I multiply across A times D and B times C. So I have the ability to get rid of a fraction using a cross product. Why is that one so special? Well, you notice that all of my parts of the law of sine include a fraction. So if I don't want to deal with those fractions, I can use a cross product to get rid of them. So, a couple theorems from geometry. A theorem from geometry, a theorem from earlier this semester in Trig, and a theorem from algebra are going to be our main tools to solving these problems. Note the three. We'll be using each one as we go through our problems today. My long-term goal with the law of sines, remember, is to find all values. I have three sides, I have three angles. When you are finished, you will have 6 answers. Now, for this to work, you'll always be given half the answers at the beginning. These are your knowns. These are what are known in the problem from the start. You are given some of the sides. You are given some of the angles. You are given something. That much is known. What you'll be tasked with doing today is using the law of sine to find the 3 that are unknown. Let's take a look at our first example. So, last time, which day? We'll be working through the law of sine. Almost everything we do today will start using one part of that formula up there. Sine A over alpha equals sine beta over B equals sine gamma over C. One part of it will involve that, and then we'll have to simplify using some or all of these pieces over here.
All.
It's possible. Depends on what you were given in the problem. So, let's take a look. We're going to set up a law of sine problem. There are actually 3 main ways law of sines start. 2 of them are very similar and are easy. One of them is a little tougher. That's the one we're going to focus on tomorrow. That's all we'll do tomorrow is the tougher one.
Just one problem.
One style of problem. So if you can usually look at the problem and tell which style it is from the very beginning by what you're given. And it depends upon how many sides you're given. Remember, you will have 3 knowns, 3 things that are given to you at the beginning. So 3 of these 6 things you will know. Which ones are missing affect how you approach the problem. Alright, let's look at the first problem. So, I'm going to use the book problem. Here's my triangle. Okay. 15 degrees is a known. 30 degrees in another angle is a known. 20 feet on one of the sides is a known. So you'll notice that I am given 3 pieces of information. Your task with, in your homework will say, find all missing pieces. Find all missing sides. Find all missing angles. Now, this is an example of an angle-side-angle problem. If you're given 2 angles to start with, these typically tend to be the easier problems. If you are given 2 angles to start with, these are the easier ones. If you're given 2 sides, these can be much tougher. That's one we'll focus on tomorrow. So, let's look at some examples. First example, step 1. We're going to find all missing pieces. up here in black is all we were given to start with. And Garrett already has one of the pieces known. What do you think it is?
The other angle.
How you don't get their angle? What is it?
135, because they all equal 180.
So, Garrett remembers, using the triangle angle sum theorem, that if I want to have a triangle, I have to have them all add up to 180. So, you can choose to show your math in this one, or you can write your solution in this one. I don't mind as much. It's a geometry concept. I'm not as worried about that one. But do make sure you are capable of doing this. So, my missing angle should be 135 because the total has to be 180. Sweet. Very nice. I have found one of the three pieces that are missing. This is why this is going to be the easier one, is because you can find one right away very easily. There are two missing sides. I'm going to find them. Now, how I do so is using the law of sines. How the law of sines works is law of sines sets up three unique fractions. Sine of alpha over A, sine of beta over B, sine of gamma over C. You will choose any two of these. Which two? Yes, doesn't matter which two. But you want to try to choose one where the fraction is knowable values. What do I mean by knowable? I mean, I can plug them into a calculator and get an answer. In this picture, I'm going to fill in the missing pieces according to this arrangement. That would mean that my 15 degrees is my alpha. My 30 degrees is my gamma. My 135 is my beta. And according to my picture, opposite of the alpha is my A side. Opposite of my gamma is my C side. Opposite of my beta is my B side. Why would I do capital B? Why would I do capital B? A B side. Identifying this relationship is good because now I can use a law of sines. Yep. So, there are three fractions. I want to point this out. There are three fractions in the law of sine. I want to use two of them at a time. Any two of them. Now, Garrett has proposed making one of those the B and beta. Why would we want to use the B and the beta?
Because you have both.
Because I already have both of those pieces. If I already have both of those pieces, that's the easiest thing to start with. So, there are three fractions for the law of sine. I have sine of alpha, so sine of 15 over A. I have sine of beta, so sine of 135 over B, which is 20. I have sine of 30 over C. I get these three fractions when I do this problem. I can only use two at a time. So I want to choose two where one of them is known and one of them contains an unknown. So we know we're going to use the beta one. I can choose to solve for A first. If I'm going to do that, I want to solve A and B as my two pieces I choose. I could choose to solve for C first. In that case, I'd use B and C as my two pieces. But either way, B is the best piece to use because I know both parts of it from the beginning. So let's do our first problem. You want to do A? Let's do A. He says, let's solve this part first. That third fraction, I'm just going to ignore it because it's not necessary to solve. In algebra, we only deal with one equal sign at a time. That second equal sign, we're just going to drop and come back to it later. Let's do it. So right now I have sine of 15 over A equals sine of 135 over 20. Sine of 15 is a number. It's a calculator problem. Sine of 135 is either a calculator problem or a unit circle problem. For this section, you're encouraged to use a calculator if you want to. Like, use it to help you as much as you need to. But don't forget, unit circle is part of your final too. But the thing that's not known is A. A is an unknown value. A is not currently listed. So my goal becomes, from algebra, if I want to solve for something, I have to get that piece by itself. I have to get A alone. Meaning A, for one, cannot be in the bottom, because then it wouldn't be by itself. And the sine of 15 cannot be with A. So, let's use the cross product property from algebra we talked about earlier. Okay? When you use the cross product, that's going to cause A to disappear from the denominator and move up to the numerator in a new location. and then we're going to work to get A by itself using algebra properties. Now, at any point in time, you may pull out the calculator and plug in sine 15, sine of 135. When I do the problems on the board, you'll notice that I don't do that until the very end. I want to do all my math in one step that I can without a calculator, and then plug on the calculator at the very, very end. That is my personal choice. I make that choice consciously because that's how I want to do it. You can choose to put the decimals in these problems if you wish to. It just means that your problem will look a little different along the way. But again, if you do your math correctly, everything should work out the same. That's our next step. I'm going to now, once I've chosen my pieces, I'm going to do a cross product. So I'm going to take sine of 15 times 20. A times sine of 135. So I get 20 sine of 15 equals A sine of 135. My goal is to get A by itself, because remember, I want to find all missing sides. I found earlier beta using the triangle sum theorem. Now my goal is to find one of the other missing pieces, A. To do that, I can have A by itself. So what do I do to get A alone?
Divide by 135.
Yeah, divide by sine of 135. To take both sides. Divide by sine 135. All the problems today and next week are going to be in degrees, so make sure you calculate in degrees when you're doing your homework. This means that my A, these two cancel. My A is equal to 20 times sine of 15 over sine of 135. This is the time when Mr. Douglas goes, that's good enough, or I grab out a calculator. If I don't have a calculator, that's the answer, I'm done. If I do have a calculator, I plug that into the calculator and hit enter. For today, one decimal place for all of your solutions. One decimal place. Since we're not dealing with radians, which typically add more decimal places, you want more accurate answers. It's all in degrees. One decimal place is perfectly fine. So I need somebody to take this number. Now, 20 sine of 15 divided by sine of 135. Plug it into that calculator and tell me what decimal values do we get.
I got 13.006 over 0.088. And then that turns into 6,503 over 44.
Are you in radians?
I don't know. Something messed up.
Dude, how do I get back to
Get back to
regular? I got 147.2.
I don't know.
Yeah, that's what you should have did.
What?
I don't know what your calculator did,
Is this what I'm supposed to do?
but now it's getting the right answer. Yeah.
Negative 10.
Mm-hmm. So I'm going to hit the conversion to get it in decimal form. The answer we got was 7.3.
Wait, how'd you get that? Oh, should I be in degrees?
Yes, make sure you're in degrees. Make sure you're in degrees. I don't know what your calculator did, but now it's working. It did sine of 135 and got a decimal that it should never get. Not even close. Like, completely wrong. What happened? Okay. Double check.
Are we in degrees on this whole?
Full sign.
Okay.
Should get 7.3. Double check with your calculator. Did you get 7.3? Take 20 times sine of 15 divided by sine of 135. If you were using the Casios, you might get a 7 greater answer. It was negative 10 plus 10 squared root of 3. But when you simplify that to a decimal, 7.3 is the solution. I am not finished until I find all missing sides. All missing angles. I found the missing angle, 135, triangle sum theorem. Thank you, Garrett. I found the missing side using this law of sine one time. I will now use the law of sine again to find the other missing side. Here we go. Go back into my picture. I'm dying up here. What the heck? All right, we found A is 7.3. So I've got one answer there. One answer there. I still need to find C. To do so, I do the law of sine again. Now, I now know 2 sides, 3 angles. I can choose to use any 2 parts of the law of sine. But I want to make sure, first of all, to use one where I include C, because that's a missing thing. But I could use C and B. I could use C and A if I wanted to. Now that I know what A is. I'm going to choose to use C and B, just to use the original information, because it's the most accurate one I should have. If I was going to use B, or if I was going to use A, it may end up being just a tiny bit off, because I'm rounding to 7.3. So, we do the problem once to find A. Do the law of sine one time, cross multiply, simplify algebraically until we find A by itself. We will do it again to find C with slightly different pieces, but it's still the law of sine, so the same setup, so the same components. So let's go over here. Let's set up the second part. So,
Question.
yes, sir.
Now that we have the A figured out, can we use that one?
Yep.
With the C?
Yep. So I would do, we could either do, these are my 2 options. I could do sine of 15 over 7.3 equals sine of 30 over C. Or I could do sine of 135 over 20 equals sine 30 over C. Either one of these will get roughly the same solution. Now, this one, the one we just found with A, a little less good because 7.3 is rounded and we know it's rounded. So it's a little less accurate. It will give us a close answer, but it might be off by a single decimal place. The back of the book might say 10.6 and you got 10.5. Okay, that's because you used the other one, which was rounded versus the original. When possible tonight, use the original. Okay?
No.
So I'm going to take this top one.
Hold on. Did you use 7.3?
All right. Let's do it. Again, I'm going to cross multiply. So take 20 times sine 30, 135 times C. So I get C times sine of 135 equals 20 times sine of 30. I get C by itself by division. So divide both sides by sine of 135. So I'm going to divide both sides by sine of 135. Left-hand side cancels. God bless you. Leaving just C. Right-hand side, I get 20 sine of 30 over sine of 135. I type that in. If I do not have a calculator, this is an acceptable solution. If I do have a calculator, I want to make sure to simplify it as far down to a single decimal point as I can. So, 14.1.
Both of the answers were the same.
Beautiful. So for this problem, whichever one you chose, you get the same solution. That's great. Do know that occasionally, if you choose a new solution, you may get a slightly off answer. I know I'm finished because I have found all 6 pieces. I have all 3 angles known, 15, 30, 135, and all 3 sides known, 20, 14.1, and 7.3. This problem is done.
That's not bad.
It's better than doing a proof problem. Once you do the proof problems, everything else in Trig is a little easier. It's like, at least it's not a proof. But I like the proof one, so I can't say too much. Okay, let's do another one. Again, my goal becomes to isolate the individual trig functions by using pieces of the law of sine to set up a simple algebraic problem. Next problem. Same piece, similar picture. Let's work through it together. Here we go. Remember the big 3? The big 3 pieces you can use to help you out. Triangle equals sum theorem, really common. Okay. The inverses, very common if you're trying to find a missing angle. We'll talk about more of those ones specifically tomorrow. And the cross product, very, very common, used almost every single time. All right, let's do it. Next problem is a triangle. Oh my God, triangle, look at that. Bottom left-hand corner, what do we have?
What?
For what problem?
Right. I got a 50 and A. So we got a 50 right there.
30.
30 in the right-hand corner.
Yes. A 10 on the round level 30.
A 10?
Yeah. B and C are open.
So B over here,
C.
C over here, and B.
B down there.
Beautiful. There are 3 missing pieces of information. Okay,
Dismounted.
we are not done until we find all 3, which means we need to find, in this case, beta, which is the top angle. We need to find B. We need to find C.
This takes up a lot of freaking paper.
Yeah, it does.
You notice I do mine side by side.
Well, I mean, yeah, I guess you're right.
To save space. So,
Beta's
beta's 100. How do you know that, Levi?
because
There we go, no reasons. Beta's 100, so 1 piece down, 2 left. Now the 2 left are missing sides. This means we're going to have to set up some kind of triangle theorem using the law of sines. So, one of these pieces is a known, the other 2 would contain at least 1 unknown. For reference, you don't have to include this in your homework, but for reference, here are the 3 pieces. According to the law of sine, sine of 50 would go with the 10. Remember, it's always opposites that go together. So the 50 and the 10 are opposites of each other. They go in the same part of the law of sines. The 30 and the C go together. The 100, which Levi found, and the B go together. My goal is to find the 2 missing sides. I do so by taking 2 of these pieces, setting up an equation, and solving. I'm going to do it once to find B, once to find C. All right. Once you get to the law of sine part of it, which one you choose to go first does not matter. Just choose one and work your way through it. So, London, B or C? B sounds good. So I have to use this first one. I have to use this first one. It's the only one that contains both things known.
Actually, no.
See? Okay.
No.
So, we're going to use these 2. I have to use sine of 50 over 10 because it's the only one where both things are known. I choose to use C because London wanted to start with C. All right. So, let's go ahead and set the left-hand side as sine of 50 over 10 equals sine of 30 over C. All right. From here, classic law of sines, first step is a cross product. So I'm going to do the cross product. I'll multiply the 2 sides in a cross pattern. So I get 10 sine of 30 equals C times sine of 50. I then want to get C by itself, so we'll use division. I divide both sides by sine of 50, getting C by itself. This gives me the following problem. C is equal to 10 times sine of 30 over 50. Now, if I had a calculator, this is an okay solution. If I use the unit circle, I can get it a little bit more reduced. But my problems all tonight say find it to 1 decimal place. So I'll grab a calculator out and type in this problem. Oh, that should be sine of 50 on bottom, not just 50.
6.5.
Come in.
What?
Sorry. Okay. Yeah, the button wasn't working. Okay.
What?
Sorry about that. All right. We have 10 sine 30 over sine 50. We plug it into a calculator. Choose 1 decimal place, please. 6.5.
You got it wrong.
Double check that, please.
I'm not on a calculator.
Does it round to 6.5? If it does, that's the correct solution. We want it to round correctly.
Oh, you got 12.9. That's how far.
Your calculator is doing some wonky stuff today, man.
I could type something wrong.
Make sure you close your parentheses and all that stuff too. Okay?
12.9 on the other.
Oh, you may have found B first.
Did you do B?
Oh yeah,
All right. Well, I guess we know what B. All right. Okay. To prove that I can use either one, I will now use the 6.5 to find B. It doesn't really matter as much. There's a chance it's a little off. So always try to go back to the original if you can, but both should get you very, very close solutions. Here we go.
It's kind of easy, not gonna lie.
sine.
Did it get harder than this or just?
Not really.
Dude, don't say that.
I told you that tomorrow we have a second type, which is a harder type because it has one twist to it.
Gotcha.
Alright, and then I have sine of 100 over b. Okay, I do a cross product. I end up with b times sine of 30 equals 6.5 times sine of 100. I divide both sides by sine of 30. I get the following. B is equal to 6.5 sine of 100 over sine of 30.
Are you doing the? Are you still doing for C?
Oh, we already found C, 6.5.
Oh, you're doing B now?
Yep, I'm doing B now.
Did you? And then you use.
Remember, I should be able to use either one.
6.5.
I use the 6.5 this time. Normally, I will go back and reuse the original information because I know that's the most accurate information, but in theory, it should get me very, very close. Within one decimal should be close. Okay?
I'm doing the other one, so we'll see.
Let's see. Alright, so for mine, I should have gotten the solution of 6.5 times sine of 100 all over sine of 30. That is a good solution if you don't have a calculator. If I give a calculator, I want to type that in and get that into one decimal place. 12.8.
See, this one I put the.
So yes, it was just a tiny bit off. Remember, you're doing odd problems, so you'll be able to see if it's a little off. And if you are a little off, my most common question will be, did you use the original information or did you use the one you found? That is the most common thing.
Doesn't matter if we're out by that much.
No. I didn't cover that. Okay. Let's set up one more. We have 5 minutes. I'll leave this one for you guys to try out on your own, so you guys can get this through pretty quick. I want you guys to try it out, see how you feel. And I'll end this for the day. Like I said, the goal, there is a second type. The second type is one where I'm given 2 sides instead of 2 angles. It's a little bit tougher, but you'll see what that's like in a moment. Here we go. Last problem for the day. Here's my triangle. Let's make this 71 degrees. Let's make this 40 degrees. Let's make this 18 meters. Why not? Here's your problem. You have 5 minutes. Find all missing pieces of information. Find the missing angle. Find both missing sides. Go, 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 go. Ah. So while you're working, my suggestions for how I will approach. My first thing I usually do when I look at a triangle like this is I try to establish their opposites relationships. Which ones are supposed to go together? Where does the 18 go? Who does it go with? Who's its dance partner? Where does the 71?
Did you just say
Who does it
dance
go with?
sponsor?
Yes, dance partner.
Partner?
Every variable needs a dance partner. Otherwise, it'll come down. I'll also, usually at the start of a problem, assign variables to anything I don't know. So like I'll be like, hey, this is going to be my alpha. This is going to be, A, because A is always opposite alpha. And I can call this B or C or something. But I want to know and keep track of which things I am currently missing. So I'll put a variable there. Most often in your homework problems, they give you a variable in that spot to begin with. If they don't give you one, put one there. Okay, there are 6 pieces missing. A, alpha, and B. Now, most of you guys earlier found the missing angle first because it's the easiest one using the triangle angle sum theorem. If you want to keep doing that, that's fine. But you could find one of these sides first if you wanted to. You just have to set up a log sign problem to do so. So my setup would be, here's my 3-part law of sine, so I'd only use any 2 of these. Sine of alpha over A. This is the worst place to start because I have 2 unknowns. So either I want to use a triangle angle sum theorem to find the missing angle, or skip it until I can find a missing side. I have sine of 40 over 18. I have sine of 71 over B. These would be my 3 parts. Once I know one of these pieces, I could fill it into this equation. So if I find out what alpha is, you can try to do the sum. I could just plug that in and have a better version of this equation. When I find A
is 69.
69,
A is 26.1.
he says 26.1.
He thinks. What's LOL mean?
What was the angle?
Yeah. Oh, dude, we got second, bro. Scarecrows for America.
Second?
Yeah.
Who beat us?
Pack.
Oh my god, that's Kalena's group. She's in our class. They only have 2 people. They good.
I don't care. We got $100,000.
They got 150 and they only have 2 people.
That's
We
true.
have to divide ours by 5.
They didn't answer any questions yesterday, though.
We still have to divide ours by 5.
Dude, chill out. It's good.
150,000. What are you talking
Fake money.
Oh.
We're
Maybe
we're,
rich.
We're
I
secretly
was
like rich.
about? There's some my way. I just want to eat good tonight. A steak dinner. Alright. Find B yet?
That sounds good.
I will here in like 25 seconds.
24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11,
I could do that.
9, 8, 7, 6, 5,
A is 26.1.
2, 1.
26.45. 26.5.
For what? A?
For B.
For B?
26 point what?
5.
26.5. And if you remember your geometry, this actually makes a lot of sense. Notice that 70 and 69 are very close in size, so their sides that are opposite them should also be close in size. This is referred to as the triangle inequality property from geometry, but that's been a little while for many of you, so I don't expect you all to remember that stuff, but do note it does make sense by the properties. So, today, law of sines. The easy ones are when you're given 2 angles. When I post the homework assignment, if you look at your problems, any problems that have 2 angles given are doable now. If they have 2 sides given, we'll talk about what that means tomorrow. It's a slightly different process because you're going to have to use an inverse than we didn't talk about today. But that is it for today.
Go up in the trailer, man.